Okay, so in continuity, here we have this formal definition, and there's kind of an intuitive understanding that you're going to develop about continuity, but in fact, this definition is what makes all that work. This is the definition of continuity. So this is the limit of a function as x approaches a is that function evaluated at a, and if that's true, then you have a continuous function. Okay, so this is by definition. It's not a theorem or anything like that. It's just saying that as the function approaches its limit, if the limit equals what the function is evaluated with a, if those two are the same, we're going to have a continuous function at that point. Okay, so notice that these are the functions that we have been calculating limits directly by evaluating f at a. So like polynomials, come to mind pretty readily. And with this definition, there's actually three things that are implied here that perhaps aren't explicitly stated. The first one is that f at a is defined. So what this means in ordinary language is that a is part of the domain of f. So we're not doing anything like dividing by 0 or taking the square root of a negative number or anything like that. So that's one of the things that this definition implies. The next thing is that the limit as x approaches a of f at x exists. Now we've seen some cases where the limit doesn't exist, and so with this definition, since this limit equals a number, then we're suggesting that it does in fact exist. And finally, it is what it says, that the limit is the same thing as the function evaluated at a. So it's a little bit of a stiff definition if you think about mathematical definitions, where it just basically lays out a formula that doesn't necessarily lend to an intuitive understanding of it unless you really kind of think about it and incorporate what it's really saying into your into your intuitive understanding of things. So let's explore this a little bit more. I'm going to take a couple functions here, and these are arbitrary functions. I'm just kind of drawing them. You can see the one on the left, it's just a smooth line. The one on the right, of course, has a gap in it, and it also has that one place, the hole, where the function doesn't exist. So if I take a point on the one on the left, I can take left-hand and right-hand limits, and they're the same as x goes to a, and that limit is what the function is, what the function evaluates at that point. And so then we say that f is continuous at a. Notice I'm saying that it's just continuous at a point. I'm not saying it's continuous over the whole function. I'm just saying it's continuous at a. Now if I look at this other one, we have a couple cases. Let's look at b first. So if I call this function g at x, if we go from the left-hand and the right-hand limit as we're approaching b, we do get to the same number. So there is a limit that is defined at b. The only problem is that it doesn't equal g evaluated at b, because g at b doesn't exist. That's the whole point of drawing the circle there. There's a hole. So we say that we're discontinuous at b. This function is discontinuous at b. And then if you look at the other side, notice that the left hand and the right hand limits are not the same. Sorry for the writing being so small here, but you can see as you're coming from the right, you're going to end up at some higher value than if you start at the left. And so we have this kind of this gap here. And so with both of these, we can say g is discontinuous at b and g is discontinuous at a. So you see there's kind of a difference in the nature of their discontinuities, but they're still not continuous. One of them is because you don't end up at the same limit. The other one is because the function isn't defined at that point. Notice that f at a, since we do have that lower value, the solid dot, that actually exists there. But the thing of it is that the right-hand limit doesn't equal what that f at a equals. So on that basis, we're not continuous. Okay, so let's look at a few functions and let's see if we can decide where they're discontinuous just from their definition. Now, the one in the book, if you look in the book, they'll have a polynomial that's already multiplied out. And just to save a little bit of time, you know, we look at these things, the nature of rational functions in their factored form, because that tells us a lot about it. So here I have something that, yeah, it's tempting to cancel out the x minus 1 in the numerator and the denominator, but that, of course, then removes the domain restriction that x can't equal 1. So this function, where is it discontinuous? It's like on the previous chart, that point B, that it is discontinuous at x equals 1 because f at 1 is not defined. Okay, if we put in a 1 here, we got 0 over 0, and that's not a defined word. So with this function, we say we're discontinuous.
Wait,
Yes.
what's the difference between like discontinuity and like the holes? Because like, couldn't you easily say that there's actually a hole at x equals 1?
Yes, and that's the discontinuity.
So they're the same.
Yeah, the hole is a way to describe why it's discontinuous at that point.
Okay.
Okay, and we'll classify discontinuities on the next slide, but
Oh.
yeah, that's exactly.
Okay.
You're really saying the same thing when you say, oh, there's a hole in the function at f equals 1. Okay, that is in the definition that we've used before. That means you're discontinuous at 1. Okay?
Mm-hmm.
Yes. Somebody else had a question back here? Guess not. Okay. All right. Let's look at another function now. So we have this, let's say if I define a point at f equals 1, or at f at 1 equals 0. Okay, so now I have a function that over all real numbers it has some definition. F has a value. Okay, do we have a continuous function at this point? All right, so then what we have to see then is the limit as we go to x, as x goes to 1, we need to evaluate that, and we see that the limit of that is 3. So as we come from the left and the right, we're looking at actually 3. So if we were to, you know, find where that hole is, you would say that that thing is at y equals 3 when x equals 1. But if we look at the definition of this thing as, well, if we look at f at 1, it's equal to 0, and 0 doesn't equal 3. So what we have is really a discontinuous function because this point isn't, the point that I added to the function is not the same thing as the point that would be defined. So let me draw this on the board just to show you what I'm talking about. So if we have this thing that looks like at 1 here, if I make my axes, if this is 1, and then the point that I've added is that when x equals 1, then f at x equals, f at 1 equals 0. And so from the function standpoint, I have a value that's defined everywhere along this function. But since my limit as I'm going to 1 isn't the same thing as when I'm at 1, you say this function is discontinuous then. So in other words, if I just arbitrarily plug the hole, I don't necessarily get a continuous function. Now, had I defined that as f at x equals 3 if x equals 1, then I would have a continuous function because then the function evaluated at 1 is the same thing as the limit as x goes to 1.
So the 0 would have had to been 3.
I'm sorry?
So the 0 down there would have had to been 3?
Yeah, for it to be continuous, but I didn't define the function that way, so it's not continuous. Now, remember what this toolkit function looks like when you graph it. You're going to have essentially that thing that looks like a volcano almost, right, with two sloping sides, a gap in the middle. And since we don't have f defined at 0, we're going to say that it's discontinuous at 0 because f at 0 is undefined. So this is the same reason that you would see in the first step, but it's a little different in the sense that it's not really a hole, it's just that we have an asymptote there instead of, if we were to graph it, we wouldn't have something like this where we would indicate a hole. We'd have to indicate an asymptote. All right, and then let's look at a function that I don't think we've talked about before, but let's take the absolute value of x over x. Okay, so if we're coming from the right-hand side, x is always positive, right, as we're going to 0. So if we go from 3 down to 2, down to 1, down to 1/2, down to 0.1, down to 0.01, you know, as we're going from the right-hand side to 0, we're always positive. So the limit of this thing, since the absolute value of x then equals x, the limit of this thing equals 1. So we're coming from the right, it equals 1. If we come from the left, though, x is always negative, and so the absolute value changes the sign of that, and so we're always going to get -1. So in other words, if x is -1, we have -1, so we have 1 in the numerator. Look at the original function here. You look at x in the numerator. If x equals -1, that would be then 1, and in the denominator would be -1. If x equals, let's say, -0.01, then the numerator would be 0.01, and then the denominator would be -0.01. So you'd always get a -1 coming from the left. And so, since these are not equal, we don't have a continuous function at x equals 0 on this thing. Even though, you know, generally we think of the absolute value as being continuous. Yes.
Why does one that exist if they're so far away from each other?
Well, the number from the right hand is some number that you know, it approaches from the left hand. It approaches another number. You'll see a graph on the next chart of this.
I was just gonna say, don't they have to? Doesn't 0 plus have to equal 0 minus for the function to exist?
No, in order for the limit to exist,
Oh, yeah. The limit.
they have to be equal. And so I'm saying the limit doesn't exist there, so we're not continuous. All right, so let's look at different types of discontinuity. I showed you in those functions that we have different reasons why we're discontinuous. So let me make the plot of some of those and we'll classify those. So if we look at the first one, the one I drew on the board, we talk about that as being a removable discontinuity. And the reason why we call it a removable discontinuity is that we could easily change the expression here to cancel out the x minus 1, and then we would have that that function that would allow us, that equivalent function that's the same as f at x everywhere except where x equals 1. We could end up calculating what the limit should be, and so if we make that kind of simplification, we get what's called a removable discontinuity. Okay, so then for that 1 over x squared, remember what that looks like. That's that thing that I described as a volcano. It's basically has an asymptote at x equals 0. We call this an infinite discontinuity because there's not a value that either side approaches. If we come from the right side, we go to infinity. If we go from the left side, we go to infinity. And so we call this an infinite discontinuity. And then the third kind, which is that I showed you with that absolute value of x over x, we call that a jump discontinuity, or some authors call that a step discontinuity. But a jump discontinuity is when the value of the function goes suddenly from one value to another, and in this case the absolute value is what triggers the sign of what is normally always either 1 or -1. It jumps from -1 to to 1. Now notice there's holes on both the top and the bottom. That's because we don't have a value that's defined at x equals 0. We have 0 over 0 in that case. So it's not only a discontinuous function, but the limit as x approaches 0 does not exist.
Does the limit exist for the other ones?
Just in the first one.
Okay. So can the limit only exist in a removable discontinuity? And not for any of the others?
I'm sorry?
Can the limit only exist if it's a removable discontinuity?
Not necessarily. I mean, we can have, well, I'm going to show you actually one that the limit does exist, but it'll be discontinuous. Okay, so we're going to look at a couple more definitions, and I'll try and highlight the words that I'm actually defining, because I don't want to make it like a dictionary entry. I want to use the words in a sentence. So we're going to say we're continuous from the right of A if that limit coming from the right side of A equals f evaluated at A. And then we're going to say a function is continuous from the left. The same thing, if we come from the left, we get to the value of that function evaluated at A. All right? So probably here the best thing to do is to have an illustration, and we'll go back to that greatest integer function. Remember that greatest integer function that we talked about last time? If we put in x, any real number x, we get an integer that is the largest integer that's less than or equal to x. And so if I look at, let's say the value 1.5, which would be x equals 1.5, which would put us right about here, then that function equals 1, right? So it's 1 is the greatest integer that's less than or equal to 1.5. So if I were to graph it, I would have this stair-step function. And so clearly there are some gaps in this function where the value jumps from one to the other. But if I use these definitions of continuous from the right and continuous from the left, we'll see that the discontinuity exists with kind of a peculiar definition. So let's say n is an integer. So if we go to any integer from the positive side, from the right-hand side, and we go to it, we're going to find that limit, so if let's say n equals 1, as x goes to 1 from the right side, so that means it goes like from 1.5, 1 1/4, 1 1/8, and it goes down to that integer 1 from the right side. So it's coming from the right going to the left. That number, the function evaluated at n, which is 1, is what the limit of the function is as it goes to n. So with this definition, or let's look at the other case. If we go to n from the right, okay, so what we find there, or excuse me, from the left, as we go to that, let's say n equals 1, let's say we approach 1 from the left, that means we're going like 0.5, 0.6, 0.7, 0.8, 0.9, and going up to 1 that way, we'll find that the limit as x goes to 1 from the negative side is actually 0, right? Because any value like 0.9 or 0.99 or 0.999, the greatest integer function gives us a 0 back. So we really don't have a function that, when we evaluate it at n, equals what that limit as x goes to n from the left-hand side. So the line above it says we have a limit coming from the right, or the limit equals the function evaluated at the right. The one from the left, we don't have that equality. So what we're going to say about these is that f at x is continuous from the right, but not the left. Now, admittedly, this is not very intuitive, right? You would think if it's discontinuous, it's discontinuous. And if you look at the graph, you think, oh, of course it's discontinuous because there's gaps. But if we start looking at continuity from one side, we can see that because we have the dot on the left-hand side, so as we come from the right to the left, we're going to consider that continuous down to that point. But if we go from any value on any of those steps to the right, you know, to the point that's on the right-hand side of that line, the open dot, we're not going to approach that. We're going to actually approach the number that we're getting away from. We're saying that that's discontinuous because we're not going to find that they're equal. Okay, any questions at this point? All right, so let's step a little further then. Okay, so a function f is continuous on an interval if it's continuous at every point on that interval. Okay, so let's think about this. Up until now, we've dealt with exclusively continuity at a point. We say the function is continuous at, you know, a, or at one particular point. Now I'm going to say it's going to be continuous on an interval, that if on that interval, if I choose any point, that I'm going to, that point is going to represent, or the function is going to be continuous at that point. So here I'm extending my definition of continuity from just talking about a single point to having sets of points, which is an interval. All right, so let's look at an example of this. So what we want to do here is we want to show that f at x equals the square root of 1 plus x is continuous on the interval 1 to 2. Okay, now your gut tells you that it should be continuous, right? Because if we take any value between 1 and 2, that thing evaluates. We're going to run into trouble if x equals negative 1 or less, because then the function doesn't exist. But we're talking about a specific interval, so we're saying, okay, is this function continuous on this interval? So the only thing that we have to work with here are the rules that govern limits, and we have a whole bunch of those. I think there's 11 or 12 of them that we went over. So I'm going to do this stepwise. So the first thing that I'm going to say is, all right, I'm going to calculate the limit as x goes to a, and a is any value in the open interval. I'm not putting a at equals to 1 or 2 yet. All right, so I'm saying any value that's in between those two values. Remember the rule that we had about limits with square roots. The limit of some expression in a square root is the square root of the limit of that function. So in other words, we can kind of stick the limit inside the square root. And then we know the limits of polynomials are just basically the limit as x goes to a of 1 is 1. The limit as x goes to a of x is just going to be a. And so here what we've shown is that, actually before I do that, here what we've shown is that if a is any value between 1 and 2, that the limit as x goes to a of that function equals that function evaluated at a. Okay, so that's the significance there. So when I'm here, you know, this is like plugging in a in our function, and then here was the limit as x goes to a, and since those two things are equal, then we know that we're continuous over every value of a. All right, so let's look at the endpoints now. If we follow the same kind of reasoning, where I'm only evaluating as x goes to 1 from the positive side, okay, so that's the right-hand limit, or with 2, if I'm looking at the left-hand limit as I'm going to 2, that those things equal what the function evaluates into. So this is a little different than the one that I had before where I'm just taking a as any value in between 1 and 2. There I'm just looking at the limits. On the endpoints, I'm only looking at the left and right-hand limit, because outside of this interval, I don't care. I don't care what happens. I don't care if it's continuous at 1. I don't care if it's continuous from the left. I only care if it's continuous from the right. And since I can do the similar kind of substitution where I can show that it's continuous from the right as x approaches 1, it's continuous from the left as x approaches 2, then we're going to say that this function is continuous over the interval 1 to 2, including 1 and 2. Now this may seem a little tedious at this point, and admittedly it is. Let me go back. I know I went too fast there. It may look a little tedious, but it's an important notion to think about a function being continuous over an interval. Because oftentimes, there are places where a function's not continuous, and we don't really care about those places sometimes. Sometimes we just care about certain intervals, like if you're making a mathematical model, you're interested in just a particular domain that isn't necessarily restricted by the function, but it's restricted by how applicable that function is to your model. For instance, if you're looking at an age of a person as, with a formula, or the height of a person, you don't really care if they're a negative age or anything like that. You care about the interval of their lifetime, 0 to, however long they live. Yes?
So it wouldn't be continuous if one of those two created a whole, right?
That's correct.
Okay. And when you're plugging something in, so like x to 2 minus, do you plug in a positive 2 or a negative 2?
Well, it's never a negative 2. What the little negative sign in the superscript means is that you're coming from the left.
Okay.
Okay, so it's where you're coming from. If I meant negative 2, I would write the negative in front of the 2.
Okay, so
Okay?
you just plug in the normal number as it is.
Well, at this point, we're not really plugging in numbers. We're evaluating these things like I did in that first step where you're evaluating it sequentially. We'll get to a theorem that allows us to plug it in. Okay? All right, everybody up with it? All right, so now I'm going to talk about a series of theorems. And these theorems will allow us to get to solutions and get to properties and get to things that we're interested in a lot faster than if we have to do it from base principles. And we kind of do this already. With algebra, you don't go back and always quote the associative or the commutative law of addition and things like that. We just have these kind of tools that we use. And so look at these theorems as places that we can start from because they've already been proven to be true in all these cases. So if f and g are continuous at a and c is a constant, then all these things are true. So then the sum of the functions are continuous, the difference of the functions are continuous. If you multiply a constant times the function, it doesn't change its continuity. If we take the product and if we take the ratio, so long as g at a doesn't equal 0, we're good there. Now this should seem like an echo to the ones that, the similar rules that we had regarding limits, where we were talking about the limit as the sum of these two functions approaches a or something of that sort. In fact, the proof of this comes or is done by using the limit laws that we had earlier and then applying them to the definition of what continuity is. So here we're not going to go through the proof of this thing, but because these limits do behave the way they do, we can make conclusions about the functions that when we add functions or when we multiply continuous functions at a certain point, that we retain its continuity, that we're not creating something that's not continuous.
For the
Mm-hmm.
is it C at that?
Yeah, CF. So C is a constant,
Oh,
and that's what I defined in the first sentence. C is a constant, so if I take a constant times a function, I get a continuous function. A constant times a continuous function gives me a continuous function. Okay, so then I can apply all these things to forms of functions that we've talked about in the last few weeks. And so we know that a polynomial is continuous over all real numbers because we know that x is continuous over all values of x, x squared is continuous over all values of x, any constant or coefficient times x squared is continuous, and so we can build up a polynomial that way, and so we end up with every polynomial is continuous, And from here on, if we're going to talk about theorems, and we need to know, is a function continuous, all you have to say is that a polynomial is continuous. We have just, at this point, asserted, and I haven't proven, but there are proofs to this, just basically said that polynomials are continuous. A rational function is continuous on its domain. So this means that any place that we're not dividing by zero, since a rational function is the ratio of two polynomials, and its domain is all the places where you're not dividing by zero. So in all those places, we have a continuous function. And root functions are continuous on its domain as well. So long as we're not doing something like taking the fourth root of a negative number or the square root of a negative number, all of those things are, all of those functions are continuous.
What do you mean by on its domain?
All the values that the function is defined at,
Okay.
all the values of x that it's... Okay, so we're going to get into some theorems, ones that have probably a little bit broader application than, maybe broader is the wrong word, but significant applications than the ones that we've had before. And so the first part of the theorem, like if I look at that first one, if f and g are continuous at a and c is a constant. So what we're saying is, you know, if these conditions exist, then this theorem is true. A lot of the theorems that we're going to have from here on are going to be like that. That if this is a continuous function, then these properties apply. This may look like just kind of a trivial kind of assertion, but it absolutely is not trivial. And oftentimes, theorems that you think are going to fail or that maybe give you a wrong answer, they don't fail and they don't give you a wrong answer. It's that you've assumed that they apply when they don't apply because you're using it on a function that isn't continuous over the region that you're interested in. So when the last theorem that we're going to talk about today is going to be called the intermediate value theorem, and continuity is huge because if it wasn't continuous, the theorem doesn't apply. And so anyway, okay, so let's look at composite functions now. We did a little bit of functional algebra. We multiplied functions, divided functions, added functions. So what happens in composite functions now? Okay, so let's say if we have a function f that's continuous at b, and the limit as x goes to a, and this should be, let me make a change here because this should be f at g equals b. This should be a g at x equals b. Okay, so if we have the limit as x goes to a of g at x equals b, then the limit of x at g at x equals f at b. All right, so here this is getting a little tricky because we're not suggesting that f has to be continuous at x equals a. F has to be continuous at x equals b. All right, so when we make composite functions, f is operating on the result or the value of f at or at g at x, and that's the value that we're interested in. Okay, so if I were to write this a little bit more compactly, I would say that the limit as x approaches a is the same thing as the function of the limit of g at x as x approaches a. So as x approaches a, we can go inside that function, and we're evaluating this, making the limit of this inner function. And that's a little bit of what I did with that one function where you have f at x equals the square root of 1 plus x. You know, I took my limit all the way inside to evaluate the limit of x directly. All right, so now another theorem that if G is continuous at A and F is continuous at G at A, then the composite is continuous at A. So if I put this in a little bit more symbolic form here, that F at G at X is continuous at A if that limit exists. So notice the first theorem, I'm only talking about limits. The second theorem is a consequence of those limits being equal, that my continuity then, that I meet my continuity question by using the first limit, or first theorem, to actually as the basis of the second theorem. All right, so let me show you an example, because I know that that this is a little abstract here. So let's say I have these two functions. My f at x is the square root of 1 plus x, and I'm looking at this at 1 to 2. So if g at x equals 1 plus x, all right, so I'm saying that what's inside the square root, I'm calling that a function, and I said that's continuous from 1 to 2. We know that's true because 1 plus x is a polynomial, and we said that all polynomial functions are continuous. So then we can say then that if h at x is the square root of x, then it's continuous from 2 to 3, because that's really where the question is, because it's not a question of what is x in this case here, in the case of x. It's not really the interval 1 to 2 that we're concerned about. G at x gives us its kind of output. The range of g at x when its domain is 1 to 2 is 2 to 3. And so here the composite function f at x is continuous from 1 to 2 because, well, first g at x is continuous over the interval that we're asking for, and then if we form an interval that's the output of g, so to speak, where does g at what does g at a equal, that we know that h at x is continuous there as well.
Wait, where did you get h of x?
I'm making them up. I'm making f at x a composite that's h at g at x.
Oh.
All right, so that's a little bit like what we did earlier when we have, the toolkit function that was 1 over x, and we say, where is that not defined? Well, that's not defined where x equals 0, so if we have a similar function that is x plus 1, we say that that is not defined where x plus 1 doesn't equal 0. Okay, and so this is the same kind of thing where we look at the range of that inner function, which is 2 to 3, h has to be continuous on that in order for f at x to be continuous at over the interval 1 to 2. All right, I mentioned the intermediate value theorem earlier. This is your first big theorem. This is one of the major theorems of calculus. We're going to have another theorem called the mean value theorem, which sounds like it should be the same thing because you think intermediate and mean are kind of similar words. They're going to be completely different theorems, and so I'm making this point so you can get the name intermediate value theorem, square what I'm talking about here. And oftentimes we just abbreviate this as the IVT. So if we're trying to prove something, you can say, well, by applying IVT, then this is true, something like that. So we can use this abbreviation. Almost everybody would in math would recognize IVT as the intermediate value theorem. Okay, so let's say, let's look at this. So suppose that f is continuous on the closed interval a to b, and let n be any number between f at a and f at b. Okay, so where f at a doesn't equal b. So let me draw a picture of what I'm talking about here. This is only the predicate, or this is only the condition of the theorem. It's not the conclusion of it. So I'm saying that we have this function that exists from A to B. It's continuous. I haven't drawn in the function yet, but I'm saying that f at A is the lower number, f at B is the higher number. It doesn't have to be that way. It could be the other way around. All I'm saying is that they're not equal. And then n is some number in between them. Okay, so this n here, it's in between f at A and f at B. So what the intermediate value theorem says is that there exists some value c within that interval A to B, and notice that's an open interval, A to B, such that f at c equals n. All right, so let me draw this. Okay, so let's say that this is a possible function. Since n is between f at A and f at B, there is some value c in between A and B that f at c equals n. Okay, so I always think of this thing as if you have two values, if you have some middle value, you have to go through the function's line. Now, if I just took a different function, let's say f at A and f at B are the same values, well, we'd have a different c, but it would still exist. Okay, so c has to be somewhere. There's no way that you can draw a function between a continuous function between f and A and f at B where n doesn't have a c that f at c gives you n. Okay, so why is this such a big deal? You know, at first this may seem a little confusing, but if you think about it a little bit more, it almost seems obvious. Okay, we're almost to the end of class, so I'm going to ask you to go to the notes that I'm going to post this afternoon. Okay, so here's an example. Let's say that there's show that there's a root of this equation between 0 and 1. So in other words, there's some value between 0 and 1 that makes this equation true. I'm not asking you to find it, I'm just asking you to prove that 1 exists. Okay, so what I'm going to do is I'm going to say, all right, let my function be that polynomial. And I'll evaluate the polynomial. Okay, it's a polynomial, it's continuous from 0 to 1. Okay, so that means I'm setting up my proper use of the intermediate value theorem. Okay, so then I'm going to evaluate f at 0. F at 0 is -6. And then I'm going to evaluate it on the other end. F at 1 equals 7. Now, in order for this thing to have a root, that means that the function is going to equal 0. And so this intermediate value, n equals 0, is between -6 and 7. So there has to be some value in between 0 and 1 that makes this thing equal to 0. All right, so if I were to draw this on the board, and whatever my function looks like, at 0, I'm at -7. At 1, I'm at 6. So in between these two values, I'm going to cross my 0 somewhere. Okay, it's like, and that's what the intermediate value says, that in order for me in order for this thing to equal 0, I'm going to do it somewhere between 0 and 1, right? And so it may be a value close to 0, maybe a value close to 1. Doesn't really matter. It's somewhere in between the two. All right. And so my closing comment is when you're using when you're making graphs by the point plot method, that means you take your function, you put a bunch of points, and you draw a line in between it. You're really kind of intuitively using the intermediate value theorem. You're saying that in order to go from here to there, you have to go. X has to go between all those values. Okay? So for those of you who came in late, I will make a PDF